Okay, so at the end of last class, we started talking about p-value, right? How to use p-value approach to make the decision, okay? And I told you that it is very convenient, and actually, in most of the real life research these days, okay, everybody uses p-value approach, right? Nobody uses critical value approach, because in order to use critical value, you have to look for the critical value from the table, okay? But if you decide to use p-value approach, you don't have to do that, okay? So you'll see and you will appreciate that convenience from p-value approach, okay? All right, and the last class we also discussed, I introduced about the t-distribution and t-test. And I believe I missed one thing here. I forgot to mention this. When using the t-distribution, you must assume the population you are sampling from follows a normal distribution. Okay? So that's the underlying condition, underlying assumption for running a t-test. Okay? But the trouble is, we don't know actual shape of the population distribution, right? So what can you do? If you have no idea, you have no reasonable ground to assume that the population is normally distributed, right? That's yellow. Okay. Then what can you do? All right. So first thing you can do is CLT. What is CLT? Central limit theorem, right? CLT can be applied when n is greater than or equal to 30, right? Okay. Because central limit theorem says regardless of population from which you are sampling from, as long as you have sufficiently large sample, the sampling distribution, in other words, the distribution of sample mean or any other the sample statistic, right, will have normal distribution. Okay? So that's one very convenient feature that we can use. Okay? If not, in other words, if your sample size is relatively small, right, and you cannot apply the central limit theorem, right, then first thing you can try is see if population can be considered reasonably normal. Okay? And the best way to do that is what? Constructing normal probability plot. Okay? Normal probability plot. If you remember about the normal probability plot, what you do is, okay, I have a couple of examples here. So from the output from the SAS system with which I'm currently doing my research, okay? And here's the regression output. And whenever you run a regression, the SAS prints out this diagnostic, okay, and gives some information about your sample. And based on the sample distribution, you can figure out whether you can reasonably assume that population is normally distributed, right? Which one is normal probability distribution? I mean, normal probability plot here. Any idea? This one looks like normal distribution. Is that what we're talking about here when we say normal probability plot? Guys. Any idea? Anybody else? This is it, right? This one. This is called the normal probability plot. Okay? So on the vertical axis, you plot residual from after the estimation. And then on the horizontal axis, this actually you have z-score, okay? Z-score, z. So if the sample was completely normal, perfectly normal, right, then you would have a perfect linear straight line here, right? But apparently this is slightly non-normal, especially towards the end of the distribution, right? Lower end and upper end, okay? Okay. So what do you do in this case? Well, another beauty or strength of the t-test or t-distribution is t-test is robust. Robust. Okay? Robust in statistics means test results are still valid even when the population is slightly non-normal. Even when the population is slightly non-normal. Okay? So that is a very useful discovery about this t-test or t-distribution. Okay? So, in practice, when we see this kind of normal probability plot, we would say, slightly non-linear, right? It's not exactly straight line, but we can still assume that the test result is pretty much valid. Okay? What are we talking about? Test result is right here, starting from chapter 13, starting from either at the end of today's class or next week. We're going to get into chapter 13, regression. Okay, and here you see the t-values, p-values, and these are the regression coefficient estimation, right? So what we can say is these t-values and these p-values are still valid, okay? So, as I said, as soon as I get this printout, first thing I look at is these p-values, okay? Is this small enough, okay? P-value is apparently very, very small, 0.0001, okay? And last class I gave you the decision rule. Okay? Reject the null hypothesis if p is less than alpha. Okay? So in order to reject the null hypothesis, you'd like to have small p values. Okay? And what this means is even if I use alpha value of 0.0002, in other words, I can be 99.98% confident, right, and still reject the null hypothesis. Well, rejecting the null hypothesis in this context means this variable is useful, okay, in my model. Don't worry about it. I'll explain it in the next chapter. Okay? Let me show you just another example. Slightly different example. I have here multiple independent variables here, and some of them are significant, some of them are not significant. In other words, this p-value here is 0.66, right? What was the dependent variable? Was the Gini, okay, Gini coefficient, okay, which measures the income inequality, okay? And in the determination of income inequality, the divorce rate is not very important, right? Because the p-value is rather large, okay? So even if I use only 40% of confidence level, I cannot reject the null hypothesis, which means I cannot claim that divorce is a very important factor that affects the income distribution or income inequality, okay? Something like that, right? All right, so here, after all the measures, you will see another normal probability plot here, okay? Again, if you look at something like this, in reality, we just say, it's okay, right? It slightly deviates on upper tail and lower tail, right, from perfect normal distribution, okay? But, we can still accept the results of this t-test, okay? And we can use these numbers to make our claim, okay? All right. Does it sound interesting? After a few weeks, right, chapter 13 and chapter 14, you'll be able to understand what all this means, okay? It's a very interesting paper, right, about the income inequality and social mobility and so on. So here the dependent variable is actually mobility, right? How easy is it for people in the lower income class to move up in the into a higher income class and so on, okay? There, apparently, divorce is important factor, which is negative, right? That means in any society, if the divorce rate is high, okay, then the mobility is low. Once you are stuck in the low income class, okay, it's hard to move up, okay, if the divorce rate is high, okay, something like that, right? All right, so that's just the preview of what's coming. All right. Okay. So what about the normal probability plot if you don't know how to do it? You can wait until next chapter. In chapter 13, we're going to have to talk about the normal probability plot once again, okay? How to construct it, because one of the assumptions, underlying assumption for regression analysis is normal distribution of errors, okay? So with the error, we will talk about how these things are distributed, okay? Or if you want to review it right now, you can go back to chapter 6, okay? Section 6.3, pages 264 to 65, okay? And at the end of chapter 6, at the end of every chapter, this textbook gives you Excel guide, okay? How to actually run the test and how to create these variables using Excel, right? So you can follow through that Excel example and try to create this normal probability plot. Okay. Okay. So here, if the sample size is large enough, you can apply CLT and just go ahead with the t-test, right? If not, first thing you can try is look at the normal probability plot, see if it's reasonably straight line. Okay? And if you can't say that, right? If the normal probability is completely different from straight line, okay, then you're out of your luck. You cannot use t-test. Okay? So in that case, use non-parametric test. Non-parametric test. Okay? Non-parametric means this test does not use any distribution. You don't have to use a z distribution or t distribution. Okay? So it's a completely different method. Okay? And this is covered in chapter 12. Unfortunately, we are not going to cover that chapter, right, in this course, because the main focus of this course is regression analysis. And regression analysis uses parametric test. We have to assume normal distribution, okay, of the population. Okay. All right, so that's one thing you have to remember about the t distribution and t-test. Okay. All right. So here's an example. Okay. Somebody claims that the average cost of hotel room in New York City is $168 per night. Okay. And you want to test this claim. Okay. So here the null hypothesis says mu is 168. Alternative says it is not. Okay. Unfortunately, we have only 25 observations. Okay. You have a random sample of 25 hotel room or the prices. Okay. And calculated the mean value. Sample mean came out to be 172.5, which is a little bit higher than 168. And the sample standard deviation came out to be 15.4, $15.40. Okay? And run the test with alpha level of 0.05. Okay? Well, here it says assume the population is normal. Right? So you don't have to, I mean, even though the sample size is smaller than 30, right? You can just go ahead and run the t-test because we are assuming, okay, the population is normal. Okay? All right, so here's the null and alternative hypothesis. You calculate the test statistic, which is t-value, right? Because we don't have sigma. We don't know the sigma, but we have to use the sample standard deviation. Other things exactly the same. The formula for the test statistic is exactly the same as before. And we got 1.46 as the test statistic. Okay? So here's our sampling distribution. Okay? And, all right? And which should be t distribution. Okay? And we got our test statistic here, 1.46, right? So in order to make the conclusion, in order to make the decision, we have to come up with the critical value. Okay? Either critical value or p-value, right? So in order to, let's try the first one first, okay? The critical value approach. Okay? So since we are using alpha level of 0.05 and we are running two-tail test here, you will set aside rejection region on both tails, right? With the 0.025, okay? As the half of alpha, okay? And you go to the t table. Close that. Here we go. And yeah, here we go. You open up a t table. What's the degrees of freedom? 24, because n, sample size is 25, right? So when you run the t-test in this context, right, well, degrees of freedom is always n minus 1, okay? Okay. Later, it changes in multiple, when we go to multiple regression or regression analysis, okay? Okay, so we have upper tail areas 0.25, 0.1, 0.05, 0.025, 0.01, and so on. And for these 6 upper tail areas, okay, we have the corresponding t-scores, okay, for various degrees of freedom. Okay, So we are supposed to use, well, we're looking for the t-score which has 0.025 on its outside, right? So we are on, this column, right? 0.025 column. And you come down to degrees of freedom of 24, right? That's 2.0639. Okay? How to use the t table to find the critical value? 2.0639. Okay? So that's how they found out 2.0639. Okay? That's the critical value. And the area outside 2.0639 on both tails, okay? Those are rejection region. Okay? So if your test statistic falls within the rejection region, you would reject the null hypothesis, right? Because if you look at the construction of test statistic, look at it, right? This is the sample mean, 172.5, and you're subtracting somebody's claim, or what the null hypothesis claims, okay? So this difference here, right, the numerator represents how much difference there is between somebody's claim and the null hypothesis, right? So you can think if the null hypothesis was true, in other words, if the true population mean was 168, right? How likely is it that when you take a sample mean will be 172.5, right? So if your sample result is pretty much different, pretty far away from what the null hypothesis claims, right? Then the probability of rejecting the null hypothesis will increase, should increase, right? You understand what I'm saying, right? So the more deviation or the more difference you have, the large difference you have in the numerator, right? You have larger test statistic, right? Either this way or this way, right? You will have larger test statistic, right? And that will increase your chance of rejecting the null hypothesis, right? Well, here, after calculating this test statistic, considering the sample standard deviation and the sample size, okay? So S over square root of n is what we call standard error. And make sure you understand the concept of standard error. It considers the variability within the sample and then the sample size. Okay? The smaller the sample size, what's going to happen to the standard error? The larger the standard error. The larger the sample size, smaller the standard error, right? So think about it. Suppose we have 1,000 observations in population, right? And first time, let's say you are selecting the sample with a very small sample size. N is 10, only 10, right? And let's say we have, to make it simple, what you have in the population are numbers going from 1, 2, 3 to 1,000, okay? And what should be the mean, population mean? Shouldn't it be something like 500? Close to something like 500, right? Either 500 or something close to 500, right? But if you take a pretty small sample, only 10 numbers out of 1,000, compare that case to another case, right? You take 100 numbers into your sample. Which one will be more accurate? Right? Or which one will have narrower distribution? Which one will have wider distribution between the two cases? Lydia? Any guess? Okay, better chance. I mean, you mean more accurate, right? So between this narrow distribution and wider distribution, which one is which? I'm sorry? The narrow one, yeah. So that is 100, and this one is 10, right? Because, when you select larger number of observation into your sample, right, it's pretty, I guess, likely that 100 numbers will come from pretty much all across the numbers, from number 1 to up to 1,000, right? You'll get to include, wide variety of numbers, right? But if you take a very small sample, it is possible that all your 10 observations come from pretty low range or sometimes pretty high range, right? There will be a lot of variability, right? That's what this wide range implies, okay? So that's why we have S divided by square root of n to represent the variability of this sampling distribution, okay? So when you increase the sample size, your sampling distribution will be narrower, vice versa, okay? All right. So compared to that, let's say, standard error, in other words, you can consider it as a pretty sample average variability in certain sample, right? Certain size sample, right? So compared to that typical, I say, I shouldn't say normal, or I think typical is a better word. Okay? Typical variability within a sample, okay? This deviation between 172.5 and 168, it's about 1.46 times larger. Right? So 1.46 falls here, right? Which is not very large number, right? But suppose your sample mean came out to be something like 200, right? Then 200 minus 168 is 32, right? And then this test statistic will be pretty large, right? Something like 3, right? Or maybe even whatever, right? So if the sample the sample mean, right, comes out to be pretty large or extremely small, in other words, far away from 168, right? Then you're going to have the test statistic either here or here within the rejection region, right? So that will increase your probability of rejecting the null hypothesis, right? That's the idea of the test statistic, right? And comparing that with the critical value, okay? Okay, so in this case, in our example, the test statistic was only 1.46. That's only not even 1.5 times the typical variability within the sample, right, of this size. Okay, so your conclusion should be: do not reject the null hypothesis. Insufficient evidence that true mean cost is different than 168. Okay, okay, that's the how we run the test. What if we want to use p-value approach here? What can you do? So here, when you use the p-value approach, everything is the same. Null hypothesis is the same, alternative hypothesis is the same, the test statistic is the same. The only difference is decision rule. Instead of saying reject the null hypothesis if the test statistic exceeds critical value in absolute size, okay? What is the decision rule? What is the decision rule? Reject the null hypothesis if P is less than alpha, right? Reject the null hypothesis if P is less than alpha. That's it. Okay? Well, in order to do that, we need to find out the p-value, right? Well, you know, p-value, what is the p-value again? I gave you a very simple definition of p-value, easy to remember. Huh? P-value is what? It's the area, size of the area outside the test statistic, right? So if you have a test statistic, negative test statistic, right? Size of the area outside the test statistic, that's p-value. So this is half of p. Here's another half of p. That's it. Okay? So how do you find that area? Well, if this was a z distribution, then it will be easy to find the that area, right? Because you know, if the test statistic 1.46, was it 1.46? Yeah. If that was a z-score, right? Then 1.46, that's 0.9279. So we're talking about this area. So you can subtract that from the 1, or you can use the other table here. It's easier to use. If you use negative 1.46, yeah. 0, 1, 2, 3, 4, 5, 6. Okay. So 0.0721, right? That would be your half of p-value. Okay. So if you multiply it by 2, that would be something like 0.14 something, 1415. Okay. Well, unfortunately, we are running t-test here, so you can use the z-table. We have a t-table here, and t-table is completely different. Okay. These numbers here are degrees of freedom. These numbers are here are the size of the area. Okay? And these are the t-scores. Okay? So we have 1.46, right? What was it? Yeah. Was it 1.46? 1.4, yeah, 1.46. Okay? So t-score here is, with the degrees of freedom 24, 1.46 is not here, right? Between 1.31 and 1.71. Okay? There is no way we can find 1.46 here. Well, in the old days, we used to teach interpolation. Right? If you want to really find out the p-value from the t-test or t-table, right? So, well, apparently, because 1.46 is between this column and this column, the p-value will be between 0.1 and 0.05, right? So what you do is you notice the distance between, we have 3178 and 7109. 3178 and what? 3109? 24. 7109. Okay? That's 1 point. Okay? So 1.46 is, I would say, somewhere around here, 1.46. Okay? So you calculate the distance. Let's say that's 2 to 8. Okay? Then, this column was 0.01, And this column was 0.005, was that? 10, 10 and 05. Okay. 10 and 0.05. Okay? So you divide this distance by 2 to 8 ratio, right? And you say that's the p-value. Okay? That's what we mean by interpolation, right? They used to do that, right? But we don't even do that even in the introductory statistics class anymore. Because first of all, that's a lot of calculation for incorrect result. Okay? Because if the distribution was a straight line, then that could work, right? This interpolation could work. But the t distribution is not a straight line, right? So if you do this interpolation, it's only approximation at best, right? And so it's not really useful result. Okay? And second reason is we use computer. Computer is so available and easily accessed these days. Everybody has computer in their hands. Your mobile phone is basically a computer, right? And I'm sure you can run some easy statistics on. I'm sure there are lots of apps you can install on your mobile phone which can do, calculate the p-value, right? So, I showed you how to calculate the p-value on Excel, right? So if you have to find the p-value on t-test, use Excel or any statistical software, right? And you can make the decision, right? Okay? All right. I think the rest is just a simple example, right? Okay. So obviously, whatever you come up with, the p-value will be greater. The one thing we are certain here is the p-value will be greater than 0.05. Okay? And actually, what we are looking for here is actually half of the p-value, right? So according to the z statistic result, right, it's going to be something close to 0.07, right? And if you multiply it by 2, your actual p-value will come out something like 1.4 or 1.5, right? So if you use 0.05 as your alpha level, your conclusion should be do not reject, right? Because p-value is not less than 0.05. Okay? If you want, you can actually try in Excel, right? And actually calculate the p-value, right? But I'm pretty sure you will get the same conclusion. Okay? All right, so the last item here today is one-tailed test. But we already talked about one-tailed test, so let me just briefly just go over this thing. Okay? Any questions so far? Okay? So one-tailed test refers to the case where the alternative hypothesis says either less than something or greater than something, right? Then your null hypothesis will be simply the opposite of your alternative hypothesis. Okay? And so depending on just looking at the alternative hypothesis, you can decide whether this is lower tail test or upper tail test. If it says less than something, it's called lower tail test because your concern is only on the lower tail. Okay? So you're going to set up your rejection region only on the lower tail, right? And if your test statistic falls here, right, then you're going to reject the null hypothesis. Okay? Whether test statistic is here or something like, let's say this was negative 1.8, your critical value, right? And if the test statistic is here, or let's say here's positive 1.8, right? that doesn't matter, right? Because all you want to know is, let's say, mu is greater than equal to certain number or less than certain number, right? And all you care is whether we can reject the null hypothesis or not, right? If you reject the null hypothesis, you're claiming that mu is less than certain number, right? That's all you need to know, right? So once it is above this critical value, it doesn't matter how high or how large your test statistic is. Okay? All right? So that's the nature of lower tail test. Okay? If your alternative hypothesis claims it is greater than certain number, then it's an upper tail test. Okay? So here you set aside your rejection region only one tail and make the decision accordingly. Okay? This is the case of upper tail. Okay? All right, so here's another example. The phone industry manager thinks the average customer cell phone bill is over $52 per month. Okay? So what the researcher is trying to prove is this alternative hypothesis, right? Average population mean is greater than 52 versus less than or equal to. Okay? Well, here sigma is unknown, so obviously we have to use t-test. Okay? Fortunately, what's the sample size? Well, looks like sample size is only 25. Okay. Yeah. Okay. So here's another 25 for sample size. So in order to use t-test, what do you have to do in this case? You cannot apply CRT because sample size is not greater than 30 or it's less than 30, right? So what can you do? 하정? Well, if you cannot apply CRT, there is one thing we can try, right? What is it? Before we give, using non-parametric test means we are giving up and we're not going to use t-test, right? But what's between CRT and non-parametric? You'd like to know whether the population is reasonably normal? How do you know? How can you test that? Check for what? Check for, what was it? Yeah, Lena? Right. What do we call that plot? Normal probability plot, right? Normal probability plot, yeah? So in order to do this question right, okay, you have to actually check for the normal probability plot, okay, using the sample, right? And see if you can reasonably assume that the population is normally distributed, right? Yeah. But let's assume that we pass that test, okay? Then you set up the null and alternative hypothesis and, calculate the test, calculate the critical value, find the critical value, and so on. So, and then you calculate the test statistic. Comes out to be only 0.55, right? So the deviation or difference between your sample mean and the hypothesized population mean is only half of the usual variation in the sample with the size 25, right? Okay? So, you can always understand it that way, right? This t-score gives you how, basically the relative size of this deviation, right, between two numbers compared to the typical variation, right, in the sample of this size, right? And it's only 0.5, right? So, here. The critical value is 1.318 with the alpha level of 0.1. Okay, yeah, I forgot to mention that. When you are running one-tail test, you are setting up the rejection region on only one tail, right? So you should use entire alpha on that tail instead of alpha divided by 2, right? Okay? So here you're using 0.1 as the probability of type 1 error, right? And your decision will be, as anytime your test statistic comes into this area, rejection region, you will reject the null hypothesis, right? Because you are willing to accept 10% probability for committing type 1 error, okay? All right, so, this time, because the sample mean was so close to the hypothesized population mean, right, that difference comes out to be only 0.55, right, of the typical variation within the sample, right? So your conclusion is do not reject the null hypothesis, okay? Which means there is insufficient evidence that the manager's claim is true, right? In other words, the average monthly cell phone bill is above $52. Okay?